Okay, so we've been doing shocks and now we've done expansion fans, right? So what we'll do today so far, actually, is the theory of the shock tube. Okay, now for that what we'll study is the unsteady motion of the shocks, right? What we've studied so far is standing normal shocks, or standing or say stationary oblique shocks, right? What we'll do today is what if these were not standing, if these were moving, okay? So basically unsteady motion. So let's see. Now what we've sort of studied so far is this. So you have, say, an object like that. Say this is an obstruction, right? You have flow, say, coming in at, say, some velocity, say u1. It intersects a certain, say, shock wave. So let's say this is the normal shock wave over here, right? And then it continues to flow in this region, say, as u2. Right now, let us say actually so someone standing, say, over here. So someone standing over here is actually seeing a stationary shock wave. Now just think about this. Now say this shock wave actually was moving. This is the shock wave, right? This is actually moving into the flow, say, with a velocity which is w, right? So someone standing here, so therefore someone standing here, so in that case, if this is moving with a velocity w, okay, which is exactly equal to u1, right, then the relative velocity between this streamline and the shock is 0. So therefore an observer standing over here is actually going to see is what we say as a standing shock, right? What he's going to see is a standing shock, right? So this is what we have done so far. Now let us do something like this. Okay, now let's say that this u1 is actually 0. Okay, so let's just say that we have, so essentially this is my region 1, right, and this is region 2. So let's come here and say we have, say, a normal shock, say like this. Okay, so this is region 1 and this is region 2 side, right, and here u1 is equal to 0 and this shock is actually moving into this region. The shock is moving into region 1 with a velocity of w, right? Now, and this region here is quiescent, right, or stagnant. So basically you have region 1 where the velocity is 0, and you have these you have the shock wave moving into it with a velocity w, and this causes mass motion of region 2. So let's just say the velocity of that in here is, say, up. Okay, this is usually, say, less than w. So in this case this is my u2. Okay, let's just call that as up. So now if you basically, so this is this is actually an unsteady case. This is actually the unsteady case. Okay, so now let us try and understand this with an example problem, right, that you actually have a flow field like this. Okay, so essentially if you were to numerically do this, it would, we will see using the problem that it would probably mean just superimposing, if you superimpose this flow field, right, with a velocity w, if you superimpose this flow field with a velocity w, then what will happen is this u1 will then become w. Okay, this becomes the velocity of the shock then becomes 0. So what we see is here, and u2 actually then becomes w minus up, right, and then that becomes similar to this standing shock. In that case it becomes very similar to the standing shock, and then we should be able to use the normal shock tables and the corresponding isentropic tables. Right, now let us do a problem and try and understand a little more about this. Okay. So say we have a problem here. Okay, so let me do the diagram. Okay, so I have right, and I have an unsteady shock like that. Okay, and this is moving, okay, into the flow field, and the velocity of this shock, okay, is equal to that, right, and say this is region 1. Okay, okay, so let's say this is region 1. Okay, and this is region 2, and let us say, so the flow properties here are given. So P1 is right, then the temperature is right, and the velocity is 0. Okay. So what we need to find out is that we have a quiescent region 1 into which a shock wave is propagating with a speed of 548.64 meters per second. So that will induce motion in this region 2. So what we need to find out, right, so V2 is essentially, this is V2. So this is, so say this is the case A. So this is case A. Okay, this is case A. So this is, okay. So now the point is that at this here, my reference frame is somewhere over here. Okay, this is my reference frame. Okay, I have a reference frame like that, and say I am standing somewhere over here in that particular reference frame. So what I see in here is exactly this picture, right? So this is a moving shock, right, with the ground as reference frame. Okay. Now, how do we transform this? Like we said, how do we transform this to the steady state case? So what we'll do there, so we can do that in two ways. Now, one is we will superimpose this entire flow field, right, with a velocity Vs equal to 548.64 meters per second to the right. Okay. So in that case, so let us do that. So for the steady state case, so what we will do is we have, okay, this is case B. So what we will do, okay, so this is my region 1. Okay, so I have let's call this dash. Okay, T1 dash is that, and now V1 dash is equal to 548.64 meters per second, and in here the flow is in this direction. Flow is in this direction. The shock is not moving anymore because Vs net velocity of the shock is 0. Okay, so velocity of the shock in this case is 0. So what we now so therefore, so P2 dash T2 dash is equal to what? Now V2 dash is, of course, like we said before, so we have basically Vs minus V2, right? Or we'll just write out the value. Okay, let's just write out the value. So which is 548.64 minus V2. Right. So, like we said here that, you know, when the shock moves into the quiescent flow, it with a say velocity w, it induces flow in this region 2. We'll call that as UP, so U2, and this obviously the velocity of this is less than that of the shock. So when I superimpose this flow with a velocity w in the opposite direction, so therefore basically the flow will start moving in the other direction. So in this case V2 dash is this, and this is moving in this way. So now what I have over here is essentially the steady state case. So we have a flow which is coming in at velocity of 548.64 meters per second, and it is moving beyond the shock at a velocity V2 dash. Okay, and we have a standing shock. Now you could also look at this in another way. What we have basically done is moved the reference frame here to here. So now we have a reference frame over here, or you can say this person, I was standing here with on the ground with respect to this reference frame. So now I'm actually riding this wave. Okay, I am actually riding on this wave and taking a look at things going on. Okay, so now basically I have moved my reference frame from here to here. So let's say that as dash. So that is essentially the difference between the in terms of calculating this. So so now let us just look at the properties. So what we need to find out is P2, T2, V2. Okay, these are the parameters that we need to find out. Let's see what we will do. So let us look at this picture over here. So what we will do here is this. So first things first. Now A1 dash. So this we are going to use this table, right? We are going to look at this picture out here, which is the standing shock, right? This is the standing shock, and so let's say this is okay. So this is the standing shock. So what we'll do is now calculate the velocity, which is T1 dash, right? So that is around right. So these values are given. So the static pressures and the temperatures, now these were given. So we have this, right. So then corresponding to this we have M1 dash, which is right. So V1 dash is again 548.64, right, and A1 is what we calculated. So what you get from here is, so as you can see, we have a mildly supersonic flow impinging on this shock wave. Okay, so now corresponding to this, okay, now corresponding to this Mach number from the normal shock tables, right, from the tables, for corresponding to this Mach number, we get M2 dash, which is 0.0 that we get and we get this. Okay, so therefore from here if we get this, then we need to we can find out what is P2 dash, right. So P2 dash with respect to that is basically P1 dash is available, right. So we get P2 dash to be equal to right. Now T2 dash is equal to around. Okay, so this is what we get. Now clearly for obvious reasons now this is the pressure and temperature, right. Now this is equal to right. So basically with respect to the, we will basically follow the steps which we have done for normal shocks before. So once we do this, we get the corresponding ratios, and then we get P2 dash and T2 dash, right. So now these pressures, now P2 dash and T2 dash is the same as P2 and T2. Think about why, right. Why should these change or should these not change? Now all we are doing from here to here is changing the reference frame. Okay, we are just changing the reference frame. Now because of that, so now the region here, however, the properties as such, we will see the static pressures or temperatures do not change. So therefore this whatever we've calculated here is the same as P2 and T2. So whatever we calculate here in terms of pressure and temperature is the same as in the unsteady case for the for this region. Okay, so again now A2 dash, right, we get this as around 402 point this. Okay, therefore now we can calculate V2 dash, right. We can calculate V2 dash, which is equal to M2 dash A2 dash, and this is around 267 point meters per second. Okay, so therefore now we can calculate V2. Okay, now we can calculate V2 from here. Okay, so from here we can get basically, okay, let's just say V2. So therefore again, so now V2 is therefore 548.64 minus V2 dash, right, and that comes out to be 281 meters per second. So we get the V2. So so as such is very not an issue here. So let's just write this down. So P2 is 290 kilonewton per meter square, then T2 is 404 Kelvin, right, and V2 is 281 meters per second. Okay, so P2, T2 and V2. So we are basically able to calculate this. Now, so like we see that the static temperatures and temperature and pressure is pretty much the same for the unsteady case as well as the steady case. That is what we have seen so far. Now let us go ahead and calculate the stagnation conditions. Okay, stagnation conditions for both these cases. Let us do this and see what we get. Okay, so now say for for the unsteady case. So for the case for the unsteady case. Okay, so now for the unsteady case, this is quiescent, isn't it? So therefore I can say that this P1 is equal to the stagnant pressure as well. Okay, similarly this is also T01. So this is for the unsteady case. So, therefore, for the unsteady case P01 is equal to okay. So, okay, then M2 right. So, in here, so this becomes, so V2 is something we know and this is gamma R T2. So, as you can see that now we found out T2. So, T2 is known, right, V2 is also known. So, if we do that, we get a corresponding Mach number which is around 0.7, which is around 0.7, right. So, therefore, now P02. So, what we are doing here is the stagnation pressure in region 1 is P01. What we are trying to calculate now is the stagnation pressure in region 2. So, P02 we can write as P02 by P2, right, into P2. Now, what we will do is we will go to the isentropic tables and corresponding to M2 equal to 0.7 subsonic, we will calculate, we will get this value P02 by P2, right, and what we get this is around 1.1387. Okay, you can check that. So, and P2 is something that we have calculated. P2 is what we already have, the static condition 290. So, this comes out to be around 402 actually. So, what you see over here is that the stagnation, so let us just mark this, okay. So, stagnation P01 is this, right, and this is P02. So, P02 is this and this is for the unsteady case. So, this is for the unsteady case. Now, let us go to the steady case now. So, let us go to the steady case, right. So, this is my due to the change of reference frame, now this is my standing shock definition, right. So, now here for this, in this case, so P01 dash, right. Now, that is equal to right. Okay. Now, the Mach number M1 dash, right. So, the Mach number M1 dash is what we calculated earlier. So, which is 1.61. Now, with respect, so for this Mach number, again we go to the isentropic tables, right, and we calculate these ratio. Now, this comes out to be around say 4.314, and what we get here P1 dash is known to us essentially. So, what we get around here is 437 kilonewton per meter square, right. So, essentially this is P01 dash. Okay. Now, the next thing is P02 dash, again similarly. So, P02 dash by P2 dash into P2 dash. Again we go to the isentropic tables and M2 dash was 0.6655. So, around that value this around comes up to be 1.345. Again this is from the isentropic tables. So, corresponding to M2 dash we get this ratio, and then this comes up to be right. So, this is my P02 dash. So, this is my Okay, so now let's take a step back and see what we are getting. Okay, now what we will see, let us sort of write this down. So so this is for the steady case, this is for the steady state case. Okay, so what we see over here for the unsteady case is that stagnation pressure behind the shock, right, is greater than the stagnation pressure in front of the shock. And what we see over here for the steady state case, that the stagnation pressure behind the shock is less than the stagnation pressure in front of the shock. Now this is expected, isn't it? This is what we have seen before. So this is what we have seen before, but what we see is that the nature of the stagnation conditions is different for the steady case and the unsteady case. Now this is happening because of the change in reference frame, right? So so this is the difference if you look at the stagnation pressures. Okay, so now let's go back again and calculate the stagnation temperatures and see how those look like. Okay, so again, say for the unsteady case, which is case A, right. So if we calculate stagnation temperatures, again T01 is basically given. Okay, so T02 is again T02 by T1 into T1. Okay, sorry, this is right. So we get this, and again this comes out to be, so we have this here. So this comes up to be, this comes out to be, okay, what did we do there? So we had a Mach number of 0.7. So M2 is 0.7. So for M2 is equal to 0.7, this comes out to be around 1.098. Okay. So again we go to the isentropic tables. We've calculated the M2, just when we calculate the pressure, stagnant pressures. So based on that, from the isentropic tables, we can get this is 1.08, and this comes out to be around 443.6 Kelvin. Okay, we get this. Now again for the, so this is for the unsteady case, right? Now for the steady case, so this is for the unsteady case. Okay, so now for the steady case, okay. So again here, so for M1 dash, which was 1.61, right? So for M1 dash, which is 1.61, this becomes T, this ratio is around 1.512, right? So then I get this T is around 436.7 Kelvin. Okay, so I've kind of really approximated this, so you can really do better calculations than me and get more correct values. Okay, I'm just basically trying to drive home certain points. So okay, so then we do this. Okay, so similarly, this is what we've been doing so far. So okay, so again this, so this value comes out to be around 1.0 A2. So again, this comes out to be around 439 Kelvin. Like I said, I've done a lot of approximations. So essentially what we see here is that for this is for the steady case. Okay. Now there is a very stark revelation here. What we see over here is that for the unsteady case, T01 is not equal to T02, right? It's not equal to 2. But for the steady case, okay, so which essentially means that a total enthalpy, okay, so stagnant temperatures here, so which essentially means that the total enthalpy is not constant across an unsteady shock wave, okay, whereas for a steady case it is. Okay, so for a here total enthalpy not same. Okay, total enthalpy is not same across an unsteady shock wave, whereas total enthalpy is conserved across a steady shock wave. So that is what we've seen from this example. So essentially what we see is that the static pressures and temperatures, they don't change. So we can just sort of superimpose the velocity and then look up the tables as we did for any normal shock wave. However, the stagnant pressures and temperatures, they are not same because total enthalpy is different because of this change in reference frame. Okay. So all right, I think we'll go ahead now and into the shock tube, which is what we wanted to which is what I wanted to start today. Okay. Now now a shock tube is actually a practical application of shock waves and expansion fans, etc. It is used widely. So we're going to kind of briefly study the theory of that. What we saw here in this particular case, that we have a flow in a steady case, what we basically see, there is a flow coming in, right. So you could now just think of the shock wave, which is moving exactly in the same velocity here. This is also moving velocity here. So this is, if you put the reference frame over here with respect to this, so this becomes stationary, and this is the flow in front is moving this way with the velocity v1, and then it is moving with v2 dash. Now there is a stark difference here though, that what we are actually seeing is that we have a quiescent flow, stagnant flow, and a shock wave is moving into it, right. That is causing the flow in this region to there is a mass movement of the mass in here in region 2, which starts moving with a velocity v2. Now we could do this. So essentially what we can do, which is the shock tube, right. So we can implement this, say, in a yes, so for a shock tube, okay, so essentially what we will have is, say, right, so we have a tube, we have a duct, say, okay, and there are two chambers in it which are separated by a diaphragm. Okay, this is separated by a diaphragm. Let us call this section as 4. Okay, let us call this section as 1. Okay, now this section, okay, has pressures of P4, T4. Okay, so essentially it could be different gases, they don't have to be the same gas, so I put the gamma as 4. So P1, T1, A1, and they could also have different molecular weights. So essentially it could be m is the molecular weight. Okay, so let's just say molecular weight to differentiate it from Mach number. Okay, so essentially this is a system that we have. So we have a tube. Okay, we can have the same gas or two different gases, right? And there are these two chambers here which are separated by a diaphragm. Okay, and then essentially this P4 is greater than P1. Okay, so in here P4 is greater than P1. Okay. Now before I start this, let us go back to this problem one more time. Now what you can see here is for a standing shock, the way we look at all the properties, the way we developed all our relationships, that we said the property changes or the properties behind the shock, etc., or the strength of the shock, weak or strong, basically is a function of the incoming Mach number, right? That's what we did. However, if I look at the unsteady case, I can't do that. I mean, this is quiescent. So there is really no Mach number property out here. So in this particular case, the change of properties is basically governed by the ratio of the pressures, the pressure ratios between the two regions. Okay. So because if you see over here, I cannot, okay, we haven't talked about a shock wave if at all, but even if there is a shock, say now, but for some reason, by some way we are able to create a shock over here. Now that is basically, that is a shock which will start moving, okay, and then it will cause changes in properties. So now the shock, the way it will move, and whether it will be strong or weak, and which way it will move to the right or to the left, basically will depend on this pressure ratio P4 and P1. Okay. So for unsteady cases, so the pressure ratio is what is dominant. Okay. So if we have this, so let's say, so if I'm going to draw this, okay, so if I say, let me draw this, so essentially what I have over here is this. Okay, so let's just say this is X, right, and this is pressure. So therefore this is P4 and this is P1. Okay, so this is it. Okay, now what we will do is we will break this diaphragm. We will break this mechanically or using some, passing electricity or voltage. So we will break this diaphragm. Then what happens? Okay, so let us come here. If I Okay, so what I have done now is I have broken this diaphragm. Okay, so what I will have in here is that there is a shock wave. Okay, there is a shock wave which starts moving into this quiescent flow, and I'm going to call the velocity as 2. So this is region 1. This is region 1 again, right? And I have an expansion fan which starts moving into this region. Okay, now this is again the region 4. Okay, okay, so let's look at this. So I have broken the diaphragm. What that will do is it will create a shock wave which starts moving to the right, and let's say the velocity of that is w. Okay, and it's also going to cause an expansion fan to move into region 4, and yes, so region 4. Now this okay, so before that, now what this is going to then cause is the region. So this in here u1 of course is 0, as we know. Now again this is going to cause, you know, as we said, mass motion of the fluid behind it. So say this will start moving at say velocity up, okay, and so again let's call this region as 2 and this region as 3. Okay. Now this is actually, this is similar to the slip lines that we spoke about, right, when there was interaction of shocks. So this is similar to that, and there is a discontinuous entropy change across this line. Okay. So across this body. So we get across this, say, a slip line. Okay. So this we can basically say as contact surface. Let's call this as, say, contact surface. So let us just draw the, so how does the pressures look like? Okay. Okay. So what we have over here is that in here again we will have, so this is the, so let us say, so let us divide these regions. Okay. So we have this in here, right, as we had done before. So let us, this region is, say, P4. Okay. So this is P4 and this is P1. Okay. So now in here, so as we had done earlier across this constant contact surface, right, the enthalpy is discontinuous, but the pressures are same. So in here, the pressures are going to be same. Okay. Now will P2 be greater than or less than P1? Let's go back here. We calculated P2 to be larger than P1. Remember this problem that we did? So this is this is for the unsteady case, and we found out that when you have an unsteady flow like this, then the pressure behind the shock is the pressure in front of the shock is actually more than that behind it. So therefore P2 is going to be larger. So therefore in here, so let's just say P2 is here in this region, right. So this is P2. Now for, okay, so just to draw this right. Okay. So let's just say this is my P2. Okay. So this is P2. Now for this region, now for this, for the third region, here the pressure is the same. So let that pressure be same over here, but this is an expansion fan. Okay. So it will gradually increase the pressure up to P4. So this is basically, so at this point it is P3. So here P3 is equal to P2, and then it increases up to P4, the pressure here. Okay. So this is essentially our shock wave. Okay. So now if I were to just look at, say, let us look at just the shock wave part of it first. Okay. So essentially what we have now in this case, right, is an unsteady shock wave which is propagating into region 1, right, and we have an expansion fan which is propagating into region 4. So what we are going to first look at is this, right, and find out the properties in these two regions over here. So similar to what we've done in the problem so far. So if we do that, Now, the governing equations, right, the governing equations, okay, let's just for the steady state case, right. So, for the steady state case we had, right, and so this is the continuity, momentum and energy equations, right. Now, as we did in the problem, what we basically what we will do out here is, now these velocities u1 and u2, by this time now you understand this is basically with respect to the wave, right. This is so the reference frame is basically if you are sitting on the wave, or for a steady state case, so the shock is not moving, it's stagnant. Okay, so we just have to keep that in mind when we look at this picture over here. So in this case, our W1 for our unsteady case here, so U1 is essentially W, right. So again, that's what we will do. We will impose the whole impose a velocity W in exactly in this direction, right. So that this becomes stagnant. So our W1 then therefore becomes our U1 therefore becomes W, and U2 becomes W minus UP, right. So if we are basically going to, now we are just going to consider the standing shock wave. So in this case, like we did in the previous case, we will impose a velocity which is W exactly in the opposite direction. So initially, okay, so initially this one U1 is 0. Now when we impose the velocity, then what happens? So if I impose a velocity like this, which is W, then U1, so new U1 is equal to W, which is in this direction, right. This new W is 0, velocity of the shock now becomes 0, and this velocity then becomes W minus UP. So now then this is exactly similar to a standing shock. So the velocity in front, which is U1, is W, and velocity beyond that, this is your U2 is equal to W minus UP. Okay, so that is just a reference change, and so what we do is put these values in here. We just put these values in here, and okay, let me sort of write that down. So what we get in terms of how the properties look like, right. Okay, so what we get in here is this. So W is W minus UP. So we get that. Then again we get okay, then we have okay. So this essentially your governing equations reduced to this. Okay. Now also, what you see from here is that this is the exact same Hunio's equation for a standing shock, and which should be the same, because in Hunio's equation we are basically relating only the thermodynamic variables often in front of the shock, and we are not really relating that to the Mach numbers, right. So now, so let's just write down two more relationships. So now for a calorically perfect gas, okay. So for a calorically perfect gas, right, and so using that, using that into this equation, we will get these two relationships, right? We will get these two relationships. Okay, and so what we are basically, what you can see over here in this, the way I am writing this, that the change in properties are essentially being related to the pressure difference across the, right. So you can see the change in temperatures is basically in terms of the pressure ratios in front and behind the shock. So that is the same for the density change as well. Okay, we will continue from this in the next lecture. Okay, thanks.